It's an alpha source, americium 241, 0.9 microcuries, about 1 microcurie, 37,000 decays per second. Emits alpha particles and 60 keV low energy gamma rays. This is on alpha detection. As you see through the plastic shield they provide for the probe, a thin plastic shield that stops the alphas completely. If we put the source near the probe, we're getting very high counts. Notice also this is a beeping, not a clicking. It's on the meter set, if you can see there on the dial, to alpha only. Now if we turn it over to alpha plus beta, we get a background which is beta gamma, even with the probe removed from the radioactive source, getting about half a count per second or something like this on alpha plus beta, those beta particles. We put the source back here. We're getting clicking now, 20 counts per second clicking at about a centimetre away. This is the effects of the gamma ray, 60 keV gamma rays. You put it closer, you can hear the beeping superimposed. You know, the beeps are alpha, the clicks are beta, or you know, Compton electrons knocked out by 60 keV low energy gamma rays, whereas the beeps are alpha particles. Now we turn it to beta only. That's just the clicking only, and that's beta particles, or rather Compton electrons knocked off, as I say, by the gamma rays, or perhaps even alpha particles causing secondary electrons which are being picked up by the plastic phosphor behind the alpha detecting zinc sulphide deposits on the scintillation screen. There's a scintillation counter, it's a very simple instrument. One of the earliest types of instruments, you just get luminous paint like zinc sulphide. You look at it in a dark room and you hold an alpha particle source near it and you get a glow from it. And the scintillation counter idea is that plus electronics to detect the light flashes, and here you've got an accelerator tube with high voltage with the radiation particles producing light flashes in a phosphor screen behind the thin mylar foil, the aluminumized foil, which stops the light getting in. Otherwise the reading would be off scale from light radiation. You don't want to detect light with a radiation counter. So the alpha particles produce a flash about 12 times brighter than the beta particles, and that's how this instrument discriminates between alpha and beta. The circuit measures the pulse height and discriminates alpha from beta. Although, of course, you get gamma rays counting as beta particles, because gamma rays knock Compton electrons, which look like beta particles, off atoms. A 1 MeV gamma ray will knock about a 0.5 MeV electron, Compton electron, off any orbital atom it interacts with. And that would mean the effect of a 0.5 MeV beta particle hitting that tube. So gamma rays do count as beta particles, although this is not the most sensitive instrument for gamma radiation. So anyway, that's the beta only. We go back to alpha plus beta again. See, if I'm about 1 centimetre away, I'm getting what appears to be beta particles, which are actually the 60 keV gamma rays. And if I put it closer, about within about 7 millimeters from the probe, it's picking up alpha particles as the beeps. Turn it back to alpha only. You can see the alpha. So this is a good audio discrimination between alpha radiation from fissile materials, or uranium, plutonium, americium, and which cause an internal hazard when held, and the beta particles, which are not a hazard in that degree. They cause a lot less ionization. And the reason why this instrument discriminates them is that the alpha particles are about 5 MeV energy, whereas the typical beta particles are a lot less than that, about 10 times less on average, about 0.5 MeV. So you have about 10 times less energy to cause the light flashes, and therefore the light flashes are a lot less bright from beta particles or gamma rays than they are from alpha particles. It's zinc sulphide detects the alpha, a plastic phosphor produces light flashes from beta particles. So a very useful instrument to discriminate between alpha emitters and beta gamma emitters.